Let's welcome our first speaker, Antti Rasila.
Thank you. So my name is Antti Rasila. I'm working at Guangdong Technion, which is the branch of the Technion Israel Institute of Technology located in Shantou, Guangdong, China, nearby Hong Kong. And first, I would like to thank the organizers about this opportunity to present this talk here. I would very much like to visit Odessa someday. I think it's a very city with its reputation of being very beautiful and it has an interesting history. So perhaps another time. But anyway, my talk is about results on boundary behavior of quasi-regular and harmonic mappings. And introduction, what I'm talking here is, I'm talking about certain boundary behavior results, which are classical and their generalizations to some classes of functions. So the first, I mentioned here a classical result of Lindelöf. So there are several results which might be called Lindelöf's theorem. The most famous one probably is one which is called also Picard-Lindelöf theorem, which is related to ordinary differential equations and initial value problems. And the other one is one which is related to topology, that any open set on the real line is a countable union of open intervals. And these are perhaps the most well-known results attributed to Lindelöf, but this is another result which is related to complex analysis and cannot be found from all textbooks, but is in some books, like, for example, in the well-known book of Walter Rudin. And it says that if you have a curve, a boundary curve, so it starts from inside the disk and ends at the boundary. And you can, for example, normalize that it ends at the point 1. And you have a bounded analytic function in the unit disk, and you have a limit along this curve, then you have a so-called angular limit at this boundary point as well, or non-tangential limit. And this means that at any angular region, it's like a triangle which terminates at this boundary point, you will have the same limit. The opening angle does affect the speed of convergence, but it doesn't affect the value of the limit. And this is a kind of classical result, and then there's a natural question that what kind of generalizations of this kind of theorem you can have if you study something like related to to analytic functions and conformal mappings, like, let's say, quasi-conformal, quasi-regular mappings, harmonic mappings, perhaps some even more general classes of mappings. And one can say that this question also makes perfect sense in any dimension. You can replace the disk obviously with the ball, and then you can replace the triangular region with some kind of like conical region, boundary cone. And one good question here is to study this problem for quasi-regular mappings and quasi-conformal mappings. So these are the natural generalizations of conformal and analytic functions to n-dimensional space in view of the generalized Liouville theorem, which says that you don't have actually like natural conformal mappings in high dimensions except Möbius transformations. Of course, you can also develop a theory based on multiple complex variables, but then it would be different from this generalization. And quasi-regular homeomorphisms, so what are these mappings? These are kind of a geometric generalization of the local behavior of these classical function classes. So basically the definition means that the small or infinitesimally small ellipsoids or spheres are mapped to ellipsoids where the aspect ratio is bounded by some quantity, this is one possible definition. Of course, you can also define it through the differential of the function, that it has this property in the points where the function is differentiable, which is almost everywhere. That is one way of approaching this question. Now, quasi-conformal mappings were first studied in the two-dimensional case by Kröch, who only studied quasi-conformal diffeomorphisms, and then it was generalized late in the 1930s by Lavrentiev to higher dimensions. And quasi-regular mappings drops this, is the same class, but it drops the requirement of homeomorphicity, replacing it with the weaker requirement that the function is kind of topologically analytic, meaning that's discrete and open. And there's, of course, this book of Reshetniak called Space Mappings of Finite Distortion in English, which has this, which is classic about this book, about this topic, but I come from this Helsinki school, so I've mostly been familiar with the work of, for example, Martio, Rickman, and Väisälä, who developed this theory a lot. And of course, my former advisor, Matti Vuorinen, is one of the much published names in this field also. So now there's a question that usually when you are working on quasi-regular mappings, you would assume that theorems of geometric nature for analytic function can be generalized in a form or other for quasi-regular mappings as well in n dimensions. However, this is not entirely the case here. So for quasi-conformal mappings, this can be proved, and it can be found, I think, from the book of Lehto and Virtanen for in the dimension 2, and the result in n-dimensional space is due to Kering from late 1960s. But it is interesting that although this classical result does not require homeomorphicity, it is enough to assume that this function is bounded. For conformal mappings, even this assumption is not needed, but in the quasi-regular case, you don't get this result in the classical form if you have a non-homeomorphic quasi-regular mapping. And there's a counterexample which is due to Seppo Rickman and can be found from his book, for example, which is relatively complicated, but he constructs a quasi-regular mapping which has infinitely many boundary values according to different curves. And then you might think that, okay, in order to draw the conclusion of the Linderoth theorem, you can assume something more and get this kind of result, and this is indeed true. And many results of this type were proved in 1980s by my former advisor Vuorinen with different assumptions on the mapping in n-dimensional space. So I will now review some of these results and some recent results here. And here I should mention that Hn is the upper half space and Bn is a unit pole, and then I use this topological index, which is basically like valency of the function, but it cannot be defined in the same way as with analytic functions. So we need this kind of a topological definition. Okay, then a fundamental concept here is something called capacity density. So this is defined through the conformal modulus, and you basically take here a sphere of some given radius, and then you take a ball, and this t here should be 2r, I think, and then you will define a ball and kind of intersect with the ball with the set you are studying, and then consider the modulus of the Kerr family connecting this set which is cut by this smaller ball to the boundary of the exterior sphere, which should have these OTs here. So here is 2r, so it's correct. But of course you can take any t here, but this 2r is convenient here. Anyway, you will get, when this r goes to 0, you will get lower and upper limit of this kind of densities of this kind of moduli, and they are called upper and lower capacity density. So they measure this thickness of the set E in the sense of conformal capacity. They are, of course, closely related to this kind of conditions you have in Sobolev spaces and so on, which kind of discuss about ability of some set to carry a solution to a Dirichlet problem and these kind of things. Okay, so starting point here is a kind of result of Vuorinen, published in 1981 in Transactions in Mathematicals of American Mathematical Society. So if you have a mapping of a ball, and then you have a positive capacity density, lower capacity density in the set where you attain the limit. It does not need to be a boundary arc. For example, if you have a boundary arc, then you always have this condition, that this low boundary capacity density is positive because it's a continuum, so it has positive capacity density. In this case, you have an angular limit. But this is not a contradiction with the Rieman's result, because it is also assumed that this set is contained in some kind of conical region there. So it's a non-tangential set. So this, in some sense, proves, for example, that this Rieman's example requires or has at least has almost all these arcs in this example are tangential, which is not actually obvious from the construction because of its complexity. But so this tangential arcs might give you different kinds of limits, but if you have a non-tangential arc or even a set with positive capacity density, which does not need to be connected, then you will get this kind of Lindelöf type result. And this is obviously an interesting result. And now we are here, the assumption is that we have a positive capacity density, so this is bound 0. Now what we have done here this year with Vuorinen and with my student Jie Huang is that we improved this result in this kind of way that we did remove the requirement that this capacity density is strictly bounded away from 0. It does not need to be bounded from below by a positive constant. Instead, it can go to 0 on the boundary, but you need then some kind of like measurand here, which makes it to go to 0. This capacity density kind of makes it to go in the limit 0 so slowly that the function kind of goes to 0 faster than what this set where it goes to 0 collapses. This is some kind of intuition to this. And this is somewhat, I think, interesting result in that sense that it says that this idea that this capacity density is bounded away from 0 is bounded from below by non-zero constant is not really a qualitative requirement. It can be relaxed. Okay, and then there are other things one can study, and one question is that, okay, you have a limit in all conical or this kind of conical sets by this definition of the angular limit, but do you have a limit in some sets which are tangential? Not all tangential set, of course, that would give you the limit, the full limit, but there is something between, and here is another result which shows that in some particular sets or which are tangential, you will have this kind of limit. And actually, this angular limit definition already gives you in some tangential sets also this, but this is another direction of generalizing this. Unfortunately, this is rather technical, but it's somehow ideal level easy to understand what this result is all about. Okay, so this is one thing that you will assume that the function is small in a set which is in some sense thick. And another possible way of studying this is to make some kind of a condition which ensures that this kind of property is true. And here is one this kind of condition is that you have that the multiple. And the idea here is, it perhaps looks very technical, this result, but the idea is not difficult to understand. So the idea is that think about the function z maps to z to the power p. So it's just a power function in the unit disk. And if you take the disk of radius r, let's say r is 1/2 or any number less than 1, and let this p grow, this p is now the multiplicity of valency at 0, then you will get that the images of this disk get smaller and smaller and smaller. So in that sense, it gives you this kind of bound for how big the image set can be locally. And if you make this function to be very small in some set locally, you can use this conformal moduli basically and moduli inequalities to extend this smallness to a bigger set. And this principle is known by the two constant theorem, or another result of Riemann. And here this is applied to points which form a geometric sequence to the boundary, and you will get this result if you have sufficiently large multiplicity. And this is somehow interesting approach in that sense that this typically functions with high multiplicity are considered to be hard. In some sense, they are hard to estimate, and because many estimates using modulus techniques, for example, tend to assume that function is as a normal close to univalent. But this is a result for functions with high multiplicity. And here is another result of this type. So here is the Lindelöf type result for which it's sufficient essentially that it is this boundary sequence, you get multiplicity going to infinity when the sequence approaches 0. And it is indeed possible from this my paper you can find there's a contributed example by Peter Lappan which shows explicit construction by using Plaske products for this kind of function, which has this kind of property. So this is not a theoretical property; it can be realized by some kind of reasonably natural examples. Okay, so this is this higher dimensional topic, and now about another direction of generalization, which is planar harmonic functions. So what are harmonic functions here? Of course, everybody knows what they are for real values, but for complex valued functions, we would require the real and imaginary part to be harmonic functions. And these functions can be called harmonic mappings. Usually you will assume something that they are univalent, but this terminology varies from paper to paper. But the main idea here is that the real and imaginary parts are not necessarily conjugate, so you don't assume the Cauchy-Riemann equations. This gives a more general class, obviously, than analytic functions. And if you are not familiar with this topic, you might assume that you don't get any function theory for this kind of functions because let's say a real valued harmonic function obviously satisfies this one. and it doesn't have any meaningful mapping properties. Everything maps to a line segment. But anyway, it is possible with some further assumptions to make this a very interesting class of functions. And usually you would write them in which is very somehow easy to see that they admit this kind of presentation as the sum of an analytic and anti-analytic function h plus g bar, and which is unique up to an additive constant. And you make this kind of assumption and take g prime over h prime then, and this is, and then you get this kind of a Schwarz function, which is for if this is sense preserving. And if you take there are several other boundary behavior results which can be studied in this context. For example, this boundary, this Cartesian boundary extension theorem that conformal mappings between Jordan domains have a homeomorphic boundary extensions. And this result is known also by result of caring to extend for quasi-conformal mappings in high dimensions. But if you think about harmonic mappings, this looks indeed really bad, because you can take essentially the argument of a Z-type mapping and put there some imaginary path and get this kind of ugly image. And it has this kind of property that one point on the boundary expands to this line segment, and this obviously does not have a boundary continuity. It has jumps, and also you can have other types of bad behavior for this kind of functions, because you might have for example, not only points which expand to line segments, but also boundary arcs which collapse to one point. If you are studying these harmonic mappings with this kind of assumptions, there are many interesting examples. I don't have time to discuss in much detail. But anyway, the question now, if you have been working with this higher dimensional quasi-regular mappings, it's natural to ask that, okay, let's assume something more, and do we get this kind of results for harmonic mappings as well? And this characterization of this harmonic mapping boundary behavior is rather hard problem, but also interesting one, and many people have done good papers about this topic. And if this dilatation defined, as I said, if it's a Schwarz function, but if it's bounded by some absolute constant k less than 1, then the function is actually quasi-conformal. And then everything in this boundary behavior works for quasi-conformal mappings like for conformal mappings. So it reduces to the classical theory, basically. But if this goes to 1, then you will get a very nasty boundary behavior. There are several good papers about this, for example, by Daud Pshuti and Abdullah Lisaik and some other collaborators. And the interesting thing there is that you will have either concave boundary. So, for example, you cannot map a convex boundary like a unit disk to a unit disk. Like boundary which is convex, you have to have some concavity there. Or alternatively, you have this kind of behavior collapsing or expansion of these boundary points. And now these results, they assume that there's some kind of like boundary arc for which this condition that this dilatation goes to absolute value of the dilatation goes to 1 is reached. And it would leave a kind of a class of functions where you would have the dilatation which touches this boundary which touches the boundary of the unit disk at one point, for example. And could you have in this kind of situations, it is unknown that could you have this kind of like quasi-conformal like behavior despite this function not being actually quasi-conformal. And this was the motivation to study this problem. And for example, here is one result of this type about this topic. So this is due to Hengartner and Schöper and Pschuti, Lisaik and Weizmann. And they studied this characterization of these jumps, and then we used this as the basis and continued this topic to further discuss this kind of results. And we did get this kind of result here, which says that if you have a harmonic univalent mapping onto a bounded and rectifiable Jordan domain, then the boundary function is discontinuous if and only if you have this kind of property. And obviously, if you have discontinuity on the boundary, like this argument of Z, you cannot, for example, have this kind of a Lindelöf type theorems, because you have from different directions different limits. Like argument of Z has different limits when you approach zero from different directions. Every direction gives you a different limit. Okay, but what is here kind of what I did not expect in the very beginning is that we have here this derivative of this H in this characterization. I hope that we could get the characterization through only this modulus property, but we did not get it. So this was still an interesting result. It appears that this quantity here is actually necessary. Okay, another result of this type. So we have discussed these Lindelöf type theorems and boundary continuity, which is related to this Carteodori theorem. But the third theorem of this type is Köbe lemma. And it says that if you have arcs which go to boundary, so in the original version you have a sequence of arcs which converge to a boundary arc in some Hausdorff distance sense or something. You will get and there is a boundary arc is not non-degenerate, so it is not the one point, and then the function goes to zero on each of these boundary arcs, then it is identically zero. This is the most original version of this result. And it was a long time ago observed that this original result can be improved by a lot. And there was a mathematician called Runge who did make further work there and found out that it's much more natural to study hyperbolic diameter of these sets, this so-called Köbe arcs, than the Euclidean diameter. And then apparently, if you can again balance the rate of convergence and of the function and the growth of these diameters of these sets where the convergence is attained. And there are several improvements of this in the literature, for example, by Vuorinen and others. But this is this kind of result for harmonic mappings. And the main interest in this result is perhaps that one that I said that the point can extend to a boundary to the image side or line segment on the image side. But it is also so that a point can collapse, or boundary arc can on the image side collapse to a point. So it's easy to construct by using even Poisson integral formula examples of functions which have both of these behaviors. And this collapsing of points is something which we want also to prevent, or kind of characterize the conditions for that not to happen. And this is something which is related to this Köbe lemma. So here is some characterization which uses these diameters. And okay, then the one other question, further question about this continuity of this boundary function is this one, and we were able to obtain this kind of result, which is a generalization of the earlier result of Schutte, Lysaik, and Weizmann, and this gives this kind of integral condition for continuity of the boundary function at the given boundary point. So this is yet another one, and it again, this contains this dilatation, so it's interesting in that sense. And other class of mappings for which this could be considered is polyharmonic functions. So polyharmonic functions are obtained if you iterate the Laplace operator, and obviously this contains, so Laplace the harmonic functions are one polyharmonic, and if you put p is equal to 2, you get biharmonic functions and so on. So you get a wider and wider class of functions, and these functions admit this kind of representation, which is in that sense interesting, that it allows using this Taylor series type, power series type techniques in studying these, although you have this kind of term which you don't kind of want there. And this, from application point of view, this p equal to 2 is interesting because it appears in some well-known physics problems. And what we did here is somewhat interesting, because it seems that this formula is kind of offers a decomposition in the terms of harmonic functions, but there is this term where you have absolute value of z, which kind of spoils everything. And the trick with what we did with this class was that we did consider this kind of functions where you remove this term dependent on absolute value of z. But now, in order to get this get a more interesting result, we replace this z with r, and this r is now a constant. So if you compare these formulas here, this formula 2 here and this one, for some value of r, this always coincides with this kind of function of this type, but this is harmonic. This is polyharmonic, but this is harmonic, and these are called the auxiliary harmonic mappings. Of course, you have an infinite family, but then you can play with that and get something interesting. And in particular, you can get that actually these kind of auxiliary harmonic mappings have the property of univalency if and only if this harmonic mapping of this polyharmonic mapping has this same property. And if you take r goes to 1, then you will observe that actually polyharmonic mappings and harmonic mappings have basically like the same boundary behavior. And now we did use this kind of result called of Kneser, which can be found in some form from many books, for example, book of Peter Duren about harmonic mappings. But there is actually in this almost forgotten paper from 1926, where this Kneser answers to a problem of Tibor Rado, that only in German language, this paper, and this one has this kind of a result of which tells about boundary homeomorphisms and harmonic extensions. And this one does not require convexity, which is frequently associated with this kind of theorems. And now we were able to get this kind of this result. So for this polyharmonic mappings, there's for harmonic mappings, one of these some kind of big results, or at least famous results, is something, it's called the Rado's theorem, that there is no univalent harmonic mapping of the disk to the the whole complex plane. And now there's a question that do we have a univalent polyharmonic mapping? And the answer is no. And this is what we did with Shruti and my former student Everodiridis, that there's no univalent polyharmonic mapping from of the disk to the whole complex plane. And this result comes quite nicely from this previous lemma and some additional considerations. And this is at least, I think, a completely new technique for proving something for this class of functions. Of course, polyharmonic class of functions has not been so much investigated, but it has significance in applications, and there are even books about this topic. Okay, and as I said, this proof, for example, this lemma kind of shows that polyharmonic functions have essentially similar boundary behavior to harmonic ones. And we did formulate these results only for biharmonic functions, but anyway, here is a result which generalizes this previous one, which I showed you already for harmonic case to polyharmonic case. Obviously, this could be generalized for polyharmonic case and not just biharmonic, but we did not do it. Just basically, perhaps I did not have time to finish or did not want to do very technical calculations. But I think that there's no problem if you would need it. It's easy to generalize. And similarly, we generalized this other as an exercise. We generalized this other case. The result is again just formulated for simplicity for biharmonic case, but obviously would work for any B. Okay, my time is starting to be up, so thank you for your attention. Here are some papers about this topic. So here is these other main papers which I referred in this talk. Thank you.
Thank you.